Hello everyone, welcome back to ECE410 class 5 part number 2. In this part we're going to talk about switching devices. So last part we have seen that switching matrix. So we represented switch as a on-off device. But there are many different types of switches can do the same job, right? So in that case, let me see what are the devices we have to use for the switching. And for the ideal switch, we assume that we don't have any losses in the switch. That means when it's off, there are zero current going through it. When it's on, there are zero voltage drop across the switch. But in reality, we have some losses because they're made out of real devices, right? So we have some internal resistance that will have some voltage drop, and also when it's off, there should become leakage current. So we need to be aware of that. Also, is have finite speed. You cannot turn on and off switch in infinite speed. So there's also speed limit. Speed limit, how quickly you can turn on and off a switch also depends on the power, how much power that switch is carrying. The more power goes through the switch, the slower the speed, because you need recovery time for the switch to go back to the neutral position, then you can turn it on. So here the switching device over here, you can see that we have small switches, two big switches. We have transistor, MOSFET, and we have IGBT, we have SCR, and all other different kinds of switches over here. You can see the bigger the size, basically more current rating and voltage rating they have. So first one is diode. Uh, Diode is in a directional device. You know that it can conduct current only one way, right? So diode can be rated for a some smaller current to a very big current, like so 1 amp to 5,000 amps, and that can switch on and off in 20 nanoseconds depending on how much current is carrying. And MOSFET is also another device, is voltage control device. The voltage rating can go from 20 to 1200 volts, and can carry up to 100 amps. Then SCR, silicon control rectifier. This is basically a diode with control. Diode doesn't have any control, but you can control this one when you turn it on. That's called gate pulse over here. If you provide a gate pulse, it's gonna turn on, but turn off will happen when its current going through is zero. That's like diode, right? Then GTU, gate turn on, is basically HCR controlled by a MOSFET. So now you have the turn on and off control. Like SCR, you have the control on when you turn it on. GTU, you can also turn off if you want. So it's a SCR controlled by the MOSFET. And triac is basically you have two SCR back to back. So not back to back, in parallel connection, but opposite direction. So that you can have the current in both direction. And IGBT is basically BJT controlled by MOSFET again. So this is isolated gate bipolar transistor, and that is a very high power device. It can go up to like 4,500 volts, and can carry an enormous amount of current through it. So the other devices we use in your power electronics device, and all of them has some like depending on current carrying capacity, it has different notation for that. So like diode can conduct current in one direction. So forward conducting, reverse blocking, cannot conduct current in the reverse direction. And IGBT is forward conducting, forward blocking. So you can control current going forward, and also control block the current going forward. So it's not, there is nothing called reverse blocking there. And GTU, forward conducting bidirectional blocking. So that means is conduct current forward, also you can block the both direction. Then you have bidirectional conducting forward blocking, FAT. So that is, you can current can go both direction, but you can only control the forward direction of the current. And ideal switch, bidirectional conductor bidirectional blocking is ideal switch. We don't have a single switch to do that, but you can combine two or more switches to make bidirectional conduction and bidirectional blocking. So in the symbol here, diode is forward conducting, reverse blocking, right? And over here, this is IGBT, forward conducting, forward blocking. This is the symbol actually for this forward conducting bidirectional blocking. And bidirectional conduction, forward blocking, this is FAT. and this is the ideal switch over here. All right. And so over here, let me see how can you combine one or two switches to make different switch. So if you have an IGBT over here, right, and if you add diode, so then you have bidirectional conduction, because look at it, you can conduction here, also conduction this way, because diode can conduct this way, IGBT conduct this way, right? So bidirectional conduction, but forward blocking. Only you can block the current going this way, but this one is not controlled, because if we have the voltage positive on the positive terminal, diode will conduct, right? So then if you combine two of these, you can make, as I said before, bidirectional conduction, bidirectional blocking. So what it means, so over here, current can go this way, right? Come in here, this is one direction, right? Forward direction. And you can also block that. If you block this particular terminal here, this IGBT, you can block that. So then if you go to reverse one, if this one on, current can go this way here and come this way. This is another direction. You can also block that one by blocking this one here. So it's can you see that both directions conducts and both direction you can block. So it's an ideal switch, but it's not quite ideal because it has losses, but it can perform ideal switch bidirectional conduction and bidirectional blocking. So why do we use them? For rectifier, we can simply use diode, right? Control rectifier, we can use SCR or MOSFET. And inverter or DC voltage, we can use bidirectional conduction and forward blocking. And for DC-DC converter, we can use those switches over here. And AC-AC converter, we need to use bidirectional conduction and bidirectional blocking. We're gonna see more of them in coming chapters. There's an example here, very quick example of a simple conversion. So if you have this circuit over here, what would be the output? Output is basically we're looking at across the motor over here, right? So what will be the output? So again, you don't want these two switches to on at the same time, because that will create a short circuit, that will create a KVL violation. Also, you don't want these two switches to be on at the same time, because that also violates KVL, right? So you can now think about the combination. If I turn on this one and this one here, so my current will go this way, right? So that means I'll get something like this. So if 24 volts over there, so I have 24 volts over here when 1 and 2 on, right? Then if I reverse that and turn on this one and also take this one out here, all right? So then my current will go this way, right? Opposite direction. So then if based on my reference, that could be that. So that means this is your voltage drop across the motor. So that is basically a AC. It's not sinusoidal AC, but it's AC, alternating current. So it's sinusoidal, not sinusoidal, but it's AC. So that's then you can filter that out to get the sinusoidal voltage out of it. So what are the ratings? So some of the ratings over here that some can carry, let's for example, this MOSFET over here, all right, can carry 50 amps, but 200 amp pulse, that pulse could be limited, normally limits to few milliseconds. Then it can drain to source voltage off state is 60 volts. That means when it's off, it can hold 60 volts. If you try to, if more than 60 volt comes like a drain to source, when it's off, that could destroy the device. And this is the RDS, resistance is called from drain to source. Resistance RDS, that will dictate how much power is dissipating that device. And off state leak current, that means if you're off, like 60 volt across it, there should be leaking current, 10 microamps. It's very small. And also 12 run on time and turn off time. That means how long it takes to go from on a state to off a state and off a state to on a state. That's the thing. So that means what I'm talking about here. is not like this. Sorry, let me clear this. When you turn it on and off, ideally is like this, right? But in real case is basically some kind of like this. So this is the time we're talking about here. So like on time, how long it take to go to on state. This is 100. This one here is 120 nanoseconds, and this one over here is 125 nanoseconds. So how long it take to go from on state to off state, off state to on state? It's not instantaneous. It takes some time. And we're going to do this practice problem in the class. And we have one more here. We're going to do this one in the class too. I think that's all. And also we have one more here. We're going to do this in the class too. So I think that's all we have for this lecture. So come back in the class with the review of this lecture so that we can do a problem and spend time on with some problem solving and concept clearing.